Hello, I'm Sheldon Axler, the author of Linear Algebra Done Right. This video discusses part 1 of the section of the book titled Decomposition of an Operator. In this video, we will be focusing on decomposition via generalized eigenvectors. Let's quickly review our standard assumptions about notation. F always denotes either the scalar field R of real numbers or the scalar field C of complex numbers. V always denotes a finite dimensional non-zero vector space over F. We will need to use the following result. Suppose T is an operator on V and P is a polynomial with coefficients in F. Then both the null space of P of T and the range of P of T are invariant under T. This is fairly easy to prove. Let's look at the proof. First, we'll prove that the null space of P of T is invariant under T. To do this, let V be a vector in the null space of P of T. Of course, that means that P of T applied to V is equal to 0. We want to see if T of V is in the same space. So we look at PT applied to T of V. The key point here is that any polynomial in T commutes with T. So we get the equation shown here. And now, of course, because Pt of V is 0, that's T of 0. And of course, T of 0 is 0. So we conclude that T of V is in the null space of P of T. After having started with V being in the null space of P of T, this is precisely what it means for the null space of P of T to be invariant under T. That completes that part of the proof. Now we need to prove that the range of P of T is invariant under T. So, suppose we have a vector V in the range of P of T. This means there exists a vector U such that V is equal to P of T applied to U. Okay, we want to see if T of V has the same property. So T of V is equal to T of Pt of U. And again, using the fact that T and P of T commute, we can rewrite that as shown here. And of course, this shows that T of V is P of T applied to something. In particular, T of V is in the range of P of T. And again, we started with a vector in the range of P of T. We concluded that T of that vector is in the range of P of T. That's precisely what it means for the range of P of T to be invariant under T. This completes the proof. Now we come to one of the most important theorems in linear algebra. This theorem gives a complete description of the structure of an arbitrary operator on a finite dimensional complex vector space. We call this result a decomposition theorem because part A says that our vector space V decomposes into a direct sum of the generalized eigenspaces of T corresponding to the distinct eigenvalues of T. Part B says that each of these generalized eigenspaces is invariant under T. And part C says that if we restrict T to each of these generalized eigenspaces, we get a constant multiple of the identity plus a nilpotent operator. This is a very powerful description of what a general operator looks like. We have already done much of the work needed to prove this result. Let's start with part B. The generalized eigenspace associated with an eigenvalue lambda sub j is the null space of T minus lambda sub j raised to the power dimension V. That's the null space of P of T, where P is the polynomial P of z equals z minus lambda j raised to the power dimension of V. But we already proved that the null space of P of T is invariant under T for every polynomial P, and that immediately gives the desired proof of B. The proof of C follows immediately from the definition of the generalized eigenspace G of lambda sub jt. Pause the video for a moment and make sure you see why that's true. That leaves only the proof of part A. We have already proved that generalized eigenvectors corresponding to distinct eigenvalues are linearly independent. That shows that the direct sum on the right side of part A is indeed a direct sum. Thus, all that remains is to show that that direct sum on the right side is actually equal to the entire space V. Please see the proof of that in the book, where it is proved by induction on the dimension of V. Now let's erase the comments about the proofs of part B and C so that we can add another result. Here it is. This result says that if V is a complex vector space and T is an operator on V, then there's a basis of V consisting of generalized eigenvectors of T. It would be nice if there were always a basis consisting of eigenvectors of T, but that is simply not true. This is a close substitute, and it's a great and easy theorem to remember. You have an operator on a finite dimensional complex vector space, then there's a basis of the vector space consisting of generalized eigenvectors. By the way, both of the results shown here are false if we work on real vector spaces. As we've seen, on a real vector space, there are operators that have no eigenvalues. Thus, those operators have no eigenvectors or generalized eigenvectors. The proof of the result on the right is easy using the result on the left. Here it is. Choose a basis for each generalized eigenspace G of lambda sub j comma t. Do that for each j. Put all these bases together to form a basis of V. Why will it be a basis of V? That's part A of the result on the left. And then one gets, therefore, a basis of V consisting of generalized eigenvectors of T, completing the proof. Now we come to defining the important term multiplicity. Suppose T is an operator on V, and lambda is an eigenvalue of T. The multiplicity of lambda is defined to be the dimension of the corresponding generalized eigenspace. In other words, the multiplicity of an eigenvalue lambda of T is the dimension of the null space of T minus lambda I raised to the power dimension of V. We now have the following nice result. Suppose V is a complex vector space and T is an operator on V. Then the sum of the multiplicities of all the eigenvalues of T equals the dimension of V. With what we've done, the proof of this is very easy. We have the following statement that V is the direct sum of the generalized eigenspaces corresponding to distinct eigenvalues. This is our previous theorem that we called the Decomposition Theorem. Thus, the dimension of V is equal to the sum of the dimensions of the generalized eigenspaces G of lambda sub j comma t. But those dimensions are precisely the multiplicities. That completes the proof. I want to take a moment here to explain some terminology that we will not be using, but that you might encounter elsewhere, so it's important for you to know it. What we are calling the multiplicity is sometimes called the algebraic multiplicity. Again, that's the dimension of the null space of T minus lambda I raised to the power dimension V, or in other words, it's the dimension of the generalized eigenspace. In general, if you see the word multiplicity with no modifier, it does mean the algebraic multiplicity. There's also something called the geometric multiplicity of an eigenvalue lambda. That's the dimension of the null space of T minus lambda I. So you can see the difference. The algebraic multiplicity is the dimension of the generalized eigenspace corresponding to lambda, and the geometric multiplicity is the dimension of the eigenspace corresponding to lambda. One more point. Many books define the algebraic multiplicity, or just the multiplicity, to be the multiplicity of the characteristic polynomial, which is something we have not yet gotten to. But the characteristic polynomial is defined in terms of determinants, and the multiplicity is the multiplicity of a root of that polynomial. That loses a lot of meaning, in my opinion. We see that actually what's called the algebraic multiplicity, as we've defined it, does have geometric meaning. It's the dimension of a certain null space. We'll see later in these videos that these two definitions agree, but I believe that this one presented here is much clearer and more intuitive. Let's finish this video by looking at an example concerning multiplicity. Define T to be the operator on C3 that you see here. The matrix of T with respect to the standard basis of C3 is now shown here. and as you can see, this is an upper triangular matrix. Thus, without doing any work, we can see that the eigenvalues of t are 3 and 8, because 3 and 8 are the numbers on the diagonal of this upper triangular matrix. It's also easy, just from the definitions, to find what the corresponding eigenspaces are, and they're displayed here. Notice each of them has dimension 1. Thus, the eigenvalue 3 has geometric multiplicity 1, and the eigenvalue 8 also has geometric multiplicity 1. Now we turn to the generalized eigenspaces of t. Let's start with the generalized eigenspace corresponding to the eigenvalue 3. We have two eigenvalues, namely 3 and 8, and we know that the sum of the multiplicities is 3 because we're working on a three-dimensional vector space. Thus, one of them has to have multiplicity 2 and the other has multiplicity 1. To see which is which, let's start by looking at t minus 3i squared. We don't need to go higher than the square power because the highest possible multiplicity is 2. And when we compute the null space of t minus 3i squared, we get the space shown here on the right in the line for g of 3 comma t. Because that space has dimension 2, without doing any further computation, we know that the other generalized eigenspace must have dimension 1, and therefore it has to equal the eigenspace. Thus we see in this case that the eigenvalue 3 has algebraic multiplicity 2, and the eigenvalue 8 has algebraic multiplicity 1. Finally, note that the whole vector space C3 is the direct sum of these two generalized eigenspaces, just as the decomposition theorem tells us it should be. One more comment about multiplicities. In this case, it turned out that the multiplicity of each eigenvalue was the number of times that eigenvalue appeared on the diagonal of the matrix when we got the operator having an upper triangular matrix. This is always the case. I'll leave that as an exercise for you to do. This concludes part 1 of the video on decomposition of an operator. If you see a small picture of a slide in the upper left corner of this slide, then you can click on it to get to the next video. If you see a small picture of part of the cover of Linear Algebra Done Right in the upper right corner of this slide, then you can click on it to get to the book's website.